In chapter unit paper 2, we discussed also the working of queues, and the original version of a queue meant that we have basically a queue is a line, and basically we have two pointers that are pointing towards the start of the queue and the end of the queue. And originally, what the original queue was that if, say, for example, by the way, there's only one place that the queue can leave, an element can leave a queue, and that means from the front of the queue. So basically, the queue operates in the first in, first out manner. So any element that is entered the queue first will remove the queue first. Okay. So by that logic, as you can see here, that A, B, C, D, E were added, and A was the first to be added to the queue, and so on and so forth. E was the last element. That's why at the end of the queue. If we consider the working of a real life queue, what that means is that the front of the enemy, so if say people standing in a line, the person standing at the front of the line will be served first in, first out. And when that person leaves the line, all of the other people will take one step ahead towards the start of the queue. So basically, what it means is that the front of the queue is not actually moving, but the entire line is moving one place ahead. Now, this is the traditional implementation of the queue, but in terms of computers and in terms of how a queue is represented inside a memory, this is not an efficient approach. What that means is that the entire list is being copied and pasted one place ahead in the memory. Now, this will result in a huge processing overhead. So each time an element leaves the queue, I'm basically shifting all of the data one place ahead. I'm copying and pasting the data. I'm copying and pasting the data one place ahead. So this is a huge processing overhead. So the solution to this processing head was, instead of shifting the data one place ahead, what we can do is we shift the pointers around. So each time an element leaves the queue, instead of shifting the entire list ahead, what we can do is we can shift the pointer one step down to point towards the position which is the next available element. So in this case, say for example, A has left the queue. So instead of shifting B to the position of 0, what we can do is we can shift this front of the queue pointer one step down to point towards B. So what this means is that every time my element is leaving the queue, I will simply shift my front of the queue pointer one place down, so that my the pointer is being moved. Similarly, if I add an element to the queue, and obviously like a line operates in real life or a queue operates in real life, what happens is that any element or any person entering the queue will enter at the end of the queue. So in this case, if I add a new element towards the end of the queue, I will add it after my end of queue pointer. So that means, again, I'm only shifting around the pointer. So in which case, if I add a new element to my end of queue pointer, that would mean my end of queue pointer will increment and point towards this place because I added a new element. Similarly, if I add another element, my end of queue pointer will move here, so on and so forth. And eventually, it is quite possible that since my front of queue pointer is leaving out empty spaces, and my front of queue pointer is moving down, and so is my end of queue pointer adding spaces, filling in spaces and moving down as well, there's a great chance that I might end up moving my end of queue pointer back to the start of the array. This is known as the wraparound effect. So basically what happened is like so, if you see here, after E, F came about, G came about, H came about, I, J, K, and each time a new element was added to the end of the queue pointer at end of queue, my end of queue pointer incremented till it reached the last of the array, and because of which it had to move back towards the top and start the wraparound and start from the top. This effect is known as a circular queue. This is how a circular queue is implemented, that instead of shifting around the data, you shift around pointers, and because of which it is quite possible the end of the queue pointer might end up start at ahead or in the array ahead of my front of queue pointer. And this is basically, it is still the end of the queue, but basically what happened to that is that it wrapped around towards the start, and this is a circular queue. So we've discussed this working in great detail in paper 2. Now let's look at how the algorithms for the queue works, starting off by creating a new queue. And adding and working on the two operations that are possible with respect to queue. One of them is known as adding an element to the queue. The second is removing an element from the queue. So again, like the stack, only push and pop is allowed. Here, only in queue is always only two operations are allowed. And again, as with stack, you have no choice whatsoever to remove specific elements. All elements have to remove based on the working of a stack. Similarly over here, if an element exists somewhere in between the line, any element, if you want to access that particular element, you have to access all of the, you have to remove all of the other elements before that, before you are capable of accessing the element that you want. So first in, first out with the queues, and last in, first out with the stack. So this is the only possibility of accessing elements you have. And again, as with stacks, you also have only two operations with queues. One is to add an element to the queue, and one is the element to remove, one is the procedure to remove an element. Now let's look at all of these procedures. But first of all, before looking at procedures, we need to see how the queue is initialized. So for example, as before, we're working with the stack, similar concept here. I have three constants: empty string, null pointer, and max queue size. So we're assigning, as before, empty string will be assigned with an empty string. Since we're using index position 0, my null pointer will have -1 in it as a constant. And since my elements, the total size of my queue is 8, my max queue size will remain at 8. So as you can see here, starting from index position 0 all to 7, this is a total of 8 elements. After which I need three variables: front of queue pointer, type integer, end of queue pointer of type integer, and number in queue of type integer. As you can see here, as this time, the author of this book, by the way, has corrected his mistake, and he has used index position 0 for the array, as opposed to index position 1, they did that mistake. So now it makes sense that why that was wrong, and they should be index position 0. So anyway, declaring a queue, my array's name is queue, starting from index position 0 all the way to 7. Why? Because max queue size is 8, max queue size -1 is 7. So starting, my array will be 0 to 7 of type string. So let's proceed towards initializing the queue, in which I will simply assign my front of queue pointer as null, because there is no data in my queue right now, and the end of queue pointer will also have null, because there is no data. And my number in queue will assign, because the number of queue, by the way, this variable is used to signify how many elements there are in the queue right now. So since there are no elements in the queue, we'll be discovering why this variable is needed, by the way. But since there are currently no elements in the queue, I will simply say that the number of queues is assigned with 0, as it should be. So that's the end of my initialized queue procedure. Now let's see how items are added to the queue. So as before, add to the queue requires a parameter. The element that you want to add to the queue, we take that as a parameter, and we will call that new item. If number in queue is less than max queue size, so what that means is that currently if I have already stored 8 items, 8 numbers in the queue, that means there is no longer any room to add elements in the queue. So it is imperative that my number in queue, the number of elements in the queue, are lesser than the max size of the queue, which is 8. So at least there has to be one place to add elements in the queue. So in this case, if my number in queue is less than max queue size, if number in queue is less than max queue size, then what we do is, then only then this procedure code can run. That means there is at least one place to add an element. But if this condition becomes false, what that means is that my number and elements in queue are either great, they can't be greater than, but they're at least they're equal to the max queue size, and you've reached the limit and there's no longer any room for the new elements to be added. So if this condition is true and there is the number of elements in the queue are lesser than the max queue size, only then this code will become. In which case, what I will, since elements are added always at the end, in which case I will do what? I will increment the end of queue pointer by 1, and I will check for wraparound if my end of queue pointer has exceeded my max queue size. So if my end of pointer, let's just say my end of queue pointer was right here at the moment, right here, and the front of the queue is empty, for example. If my end of queue pointer was right here at this at index position 7, now after incremented, it becomes 8, right? So that means instead of moving towards, there is no index position 8, what we'll have to do is I will wrap around to the start. So to check if a wraparound is needed, I'll have to see that if incrementing my front of queue pointer results in a number that's greater than my max queue size or the greater than my last index position, then I will proceed towards a wraparound. So that's what's happening here. If my end of queue pointer is greater than index position 7, that means I have reached the end. I incremented my end of queue pointer, and because of which now I have reached a position which is greater than my last element, in which case wraparound is needed. So end of queue pointer, if it's greater than 7, that means I am accessing index position which is not existing. 8 does not exist. I have to do a wraparound, in which case what I will do is I will move towards the start of my queue, which is end of queue which is index position 0. And how I'll do that, I will simply assign end of queue pointer 0 to point towards the 0th position as the end of queue pointer. So kind of like what would have happened if I added an element I, for example. If let's just say after h, which is my end of queue pointer is at 7, after element h, I wanted to add element I. By the way, my end of queue pointer would have been here somewhere. My end of queue pointer would have been here. After adding h, my end of queue pointer would be here. Now I want to add another element I, and I have room here. I want to add another element I. So first I will proceed towards incrementing end of queue pointer. So currently my end of queue pointer is 7. Incrementing end of queue pointer result in 8, which is greater than max size minus 7. Sorry, max size minus 1. So it is greater than this. That means I'm here somewhere. And I should wrap around, in which case my end of queue pointer will come back up to 0. Now my end of queue pointer is here. I will assign that element here. Now I added I, and my end of queue pointer is now pointing towards index position 0. Wraparound took place. So if wraparound did take place, I will move towards the start of my array by assigning the end of queue pointer with 0. And simply in my queue at this index position, which is 0, I will simply assign the new item that was passed as a parameter. And since I now added an element to my queue, I will increment the number in queue with 1. This is the counter that signifies how many elements have been added to this. Number in queue is incremented by 1. So this procedure handles how elements are added to a queue, taking care of possible wraparounds if needed. Similarly, we will check this out. If we want to remove an element from the queue. So again, this is a function. So what by removing it, I mean I will simply access the the front of the queue, whatever it is at that moment, and this function will simply return the value stored at the index position signified by the variable front of queue pointer. So I will need a local variable as we did for popping an element in stack. So I will need a local variable over here as well. I'm going to call it item of type string. I'm going to assign that as an empty string. If number in queue is greater than 0, that means there are elements in the array. If there are no elements in the array and number in queue is 0, what are you going to remove from the queue? There's nothing to remove. So there has to be at least one element to remove from the queue. So we're checking that here. If the number in queue is greater than 0, that means there is at least one item in the queue and removing it from the front of the queue. So what we'll do is simply access the front of the queue pointer at that moment, access the front of the queue pointer, because obviously my front of the queue pointer is pointing towards the first element that is ready to be removed. So in my array, I will access that index position. I will take that value and assign it to the variable item. Since the element has now left, my front of the queue pointer has to come down. So as you can see here, my front of the queue pointer will move about. Now, first of all, since an element has left my queue, I will decrement my number in queue by 1 because there is one lesser item in my queue right now. So I will decrement my number in queue by -1. If number in queue has now become 0, I will simply state that my queue has now become empty, and I am now going to reset my queue to take in fresh values the next time around. So simply what we'll do is, if the number in queue has now become 0, that means my queue has become empty. I will reset the pointers, and how I will do that, I will call the initialize queue subroutine, which is this one that we're going to try to here. So simply assign everything as null and number in queue to 0, meaning that now your array is going to start from blank. There were no more elements. However, if this is not the case, and there are still elements in the array, in which case what we'll do is that we will increment the front of queue pointer, +1, see right here. If I remove this element from this queue right here, my front of queue pointer is right now pointing towards 0. Removing this element will cause the front of queue pointer to be incremented to point towards this position right here. So we have to increment front of queue pointer to point towards this position here. So having said that, if we are removing an element from the array, we will first increment the front of queue pointer like so, and we will check for a wraparound. So if front of queue pointer sorry, right here. If front of queue pointer is incremented, if front of queue pointer is greater than max queue size, so -1. So if front of queue pointer was at currently position number 7, let's just say the front of queue pointer was currently at position 7. Now incrementation causes it to go to 8, which is not part of my array. So if my front of queue pointer is greater than max queue size, which it is now, 8 is greater than max queue size, which max queue size -1 is 7. So if front of queue pointer is greater than max queue size -1, which is 7, then that means wraparound has to take place. In which case, what I will do is I will wrap around and bring my front of queue pointer back to 0. Now, see what's happening here. Imagine that this front of queue point, this is my front of queue pointer right now. If I remove F, my front of queue pointer will be incremented to point towards 6. If I remove G, my front of queue pointer will come here to point towards position 7. Now, this is the condition that will cause wraparound for the next time around. If I want to remove H, my front of queue pointer will increment to point to a value which is greater than the max size -1, yani 7. So that means I will require wraparound. So in that case, my front of queue pointer will no longer be 8. There is no 8. It will have to wrap around to all the way index position 0. So that's why wraparound is taking place over here. So that's exactly what has been taken care here. So if my front of queue pointer already was at the last index position, and after incremented results in a value that is greater than the max queue size, then that means I will have to wrap around to the start position, because we're looking at a circular queue. In any case, when I'm done with all of this and I have the item that I just removed from my queue that is in the variable item, I will simply return that item. And that is the end of the process whatsoever.